All right, well, it's been a long semester, but of course we can't finish it off without one more exam. Time to do a practice final exam. So let's get going. Now, as far as the instructions go, you'll see it's essentially the same as we've seen in the other exams, which shouldn't be so surprising. We still get our table of Laplace transforms. The biggest change is that now we're going to get 8 problems. All right, even more chances for us to demonstrate our knowledge. And well, let's go ahead. We'll put our name and we will get going. Let's see what happens. I'm excited. All right, our first problem. Solve the following initial value problem. 4xy y prime is equal to x squared plus 4y squared, and y of 1 equals 1. Now this is going way back, right to the very beginning of our class. We're like, okay, do we remember how to do this? I hope so. And now it's a first order differential equation, and it says solve. Now the good news is if we have first order differential equations, there's 3 general categories. There's linear first order, homogeneous, and separable. Now separable would mean that we could actually separate, and usually whenever you see a plus sign is an enemy of separation. Separation works best when things are multiplying together, so it's not separable. And homogeneous, it almost has to be totally clear that it's homogeneous, and this one turns out not to be that. So we're thinking it's probably linear first order. Probably. But there's a problem here. That y squared, that's not being very linear friendly. Well, that's all right. We're not going to give up. What will we do? Well, oftentimes when you see problems like this, we start by saying, all right, what should we do? Well, one thing to do is to solve and get the coefficient of y prime to be 1. So let's divide everything by 4xy. Then let's see what that does. So we have y prime is equal to, and here when we divide by 4xy, there's an x, so we get a little bit of cancellation. So we'll get x over 4y, and then here we'll get 1 over x times y. Or we could write this as y prime minus 1 over xy is equal to, I'll write this as x over 4 y to the negative 1 power. And why write it in this way? Well, because this is something very particular. So if we didn't see that y to a power, we would say, aha, this is great. We know what this is. This would be a linear first order. Life is good. But you see y to a power, and we're like, oh, interesting. Well, the good news is we know how to handle that. And this is what we have called Bernoulli. So this is going to be a Bernoulli differential equation. Now, of course, the trick is, what happens? Do we remember? Well, so the way it works is, in general, if you have y prime plus p of x y equals q of x y to the n, then our substitution, and this is how Bernoulli works, we substitute, we introduce a new variable, let's call it z, and we'll have it y to the 1 minus n power. And then we proceed. And what's going to happen is it's going to transform into a proper first order differential equation in terms of our variable z. Okay, so there we go. Now in our case, our n is negative 1. So we're going to have 1 minus minus 1, which means that we need to substitute z equals y squared. Okay, so this is the key idea. Now, where do we make this substitution? Well, we could make it anywhere. So we could put it up here, or we can even go back to the beginning. It doesn't really matter. The point is, somewhere we're going to make this substitution. And, well, if z equals y squared, well, that says z prime is 2y y prime, just taking the derivative of both sides. And now we can start saying, oh, hey, here's an idea. So let's go back all the way to the beginning. And what do we see? There's a 4y y prime. Well, that's almost 2y y prime. It's just off by a factor of 2. So we can write this as 2x z prime. So that's the first term, equals x squared. Well, that stays the same. We're only changing things with y. And then the y squared becomes z plus 4z. And now you'll notice this is perfect, right? Because what can we do? Well, we can say 2x z prime minus 4z equals x squared. Divide everything by 2x. Z prime minus 2 over x times z is equal to x over 2. All right, great. Well, now it is a proper linear first order, which means that we need an integrating factor. Because remember, the idea of linear first order says, hey, let's make the left-hand side look like a derivative, and derivatives are easy to integrate. And so the way that this works is we come here and we look at this part in the front, and what we're going to do is we're going to take e to the integral of that term. So that's what goes there. So in our case, what do we have? Well, we're going to have e to the integral negative 2 over x dx. Well, that's e to the minus 2 natural log x. Okay, well, now you might say, wait, what about the plus c? You don't need plus c, right? Plus c, well, doesn't affect the answer. And so we just make our constant simple. And, well, the minus 2 goes up as an exponent, so this is the same as x to the minus 2 power, or if you like, 1 over x squared. All right, so we now multiply everything by 1 over x squared, and what do we have? Well, we have the following. 1 over x squared z prime minus 2 over x cubed times z is equal to, and now we have 1 over 2x. But by design, this left-hand side is a derivative. It's the derivative of 1 over x squared times z. And you can check, right? The first times the derivative of the second, 1 over x squared z prime. The derivative of the first, we'll think of it as x to minus 2. Minus 2 comes down, x minus 3, that's over x cubed times z. All right, so that's equal to 1 over 2x. And now we say integrate. So we're like, great, let's do that. So we do. And what do we get? Integral. And so we get 1 over x squared times z is equal to, here we get 1/2 log x plus, of course, some constant c. All right, or we can multiply both sides by x squared. Z is equal to 1/2 x squared log x plus some constant x squared. Okay, ran out of a little bit of space there, but are we done? No, not quite, because z is y squared. All right, so we're almost there, So we now come, we can say, all right, great. Y squared is 1/2 x squared natural log of x plus some constant x squared. But remember, this is an initial value problem. Y of 1 equals 1. So now we can plug in x equals 1 and y equals 1. Now, when x equals 1, natural log of 1 is 0. That term goes away. So we end up with 1 is equal to 0 plus c. Okay, great. So c equals 1. Now, one other thing is we want to solve for y. So we have y squared. So what do we need to do to get y? Well, we take the square root. Now, here's a little subtlety. When we take the square root, there's really two possibilities, plus or minus. So which one do we take? And why is it the plus? We take the plus. And the reason we take the plus is we want our answer to have a positive 1 value when we plug in 1. If we take the minus, it'll have a negative value. So our final answer, y is the square root of 1/2 x squared natural log of x plus x squared. And there we go. There we go. That's not so bad. That's not bad at all. All right, well, good. Nice practice. Ready to, get us going. One problem down. All right, well, let's keep going. On to our next problem. Number 2. Suppose the population P of t of an ant colony grows at a rate proportional to the population. Suppose that the initial population doubles in 3 weeks. Okay, so the first sentence says, hey, we are talking about our growth, and we know we're talking about growth and rate. So you see that word grow and rate? Okay, so that's saying, how are we changing? And it says proportional to the population. So our rate that's equals proportional, some constant, to the population. Okay, so that's our setting. We're like, oh, we recognize that. Anything that has exponential behavior has that type of behavior, where the population growth, the rate, is proportional to the current population. And it says, okay, the initial population doubles in 3 weeks. Now, okay. We should make a note. There's 2 parts. How long will it take for the population to become 10 times the initial population? And then there's part B. If the initial population is P0, write down an initial value problem for P of t. Well, we actually pretty much just did that. So the initial value problem, well, that says P prime is some constant P, and P of 0 equals P0. Now, are we done? No, we have to talk about K. So that's going to come up here. Suppose that the initial population doubles in 3 weeks. So let's talk about that. What that tells us is that, let's have our time. So the question is, how do we measure time? And the problem doesn't actually tell us that. So we get to make a choice here, and we just have to be consistent. And so, since it doesn't give us an explicit declaration of what t is, let's assume t is weeks. So I'm going to finish part B, and then I'll come back to part A. You're allowed to move and go in the order that you want on problems. So there's no problem with doing that. So we were told that our population at time 3 weeks is double the initial population. So that's what it means to say our population doubled. We're doubled where we started. Okay, well, if you remember, P prime equals Kp. This is one of our basic models, so we know that P looks like some P0 e to the Kt. So we can plug this information in, and we can say, okay, so 2P0 is equal to P0 e to the 3 times K, right? Because we're plugging in T equals 3. So K times 3, 3K. Notice it doesn't matter what the initial population is. Not a surprise. That's the nice thing about exponential growth in the K. It doesn't really matter the initial population in terms of things like how long does it take to double. Okay, so we're almost there. We just need to solve for K. All right, so that says log of 2 is equal to 3 times K, or K equals 1/3 natural log of 2. So, with this in mind, we now can answer B completely. So, we get the following. we have that p prime is equal to 1/3 natural log of 2 times p, and that p of 0 equals p0. And good. Done. But now we have so much more, right? Now we can answer part A. How long will it take for the population to become 10 times the initial population? All right, well, that says we want to know for what value of t does p of t equals 10 p0. All right, well, now we say, okay, we know how things behave. We know that our p of t has this form, p0 e to the kt. We know what k is. So we want p0 e to the kt is 10 times p0. And again, the p0 cancels off. So it doesn't matter what the initial population is. It won't change the amount of time it takes. Well, get the kt out because we're trying to solve for t. So take natural log of both sides. K times t equals natural log of 10. But now we can come back and say, well, we know what k is. So we have 1/3 natural log of 2 times t is natural log of 10. And now we're almost there. We just need to solve for t. So we get that t is 3 natural log 10 divided by natural log of 2. So we moved those terms across. And we'll throw in weeks, so there's no ambiguity. And that's the answer. There we go. Now you might say, what is that? Exactly. What's the exact decimal value? And we don't know. We'd have to use a calculator. Well, calculators aren't allowed. So we want to be comfortable with, just saying, look, this is our answer. We'll leave it in this format here. Now you might wonder, can we say anything about this number? Well, actually, we can do a little bit, right? Because we know how long it takes to double. So if it doubles in 3 weeks, then after 6 weeks, I'll have doubled twice. That means I'm 4 times. After 9 weeks, I'll have doubled 3 times. That means I'm 8. So it takes more than 9. After 12, I'll have doubled 4 times. I'll be up to 16. So it's somewhere between 9 and 12 weeks. So that's what we can say definitively. Okay, that's not so bad. We have it within a 3-week window. And, well, there you go. So, again, nothing too surprising, and we should be comfortable with doing these types of problems. All right, well, great. We're making wonderful progress. So, solve the initial value problem. Y double prime minus y is equal to 2x plus e to the x, and there's some initial conditions. Y of 0 equals 1, y prime of 0 equals -1. Now, before we jump in, let's make sure we know what we're doing and what our game plan is. Now, there's a couple of things that we see. We see, of course, y double prime minus y over here. This is nice. This is a linear, constant coefficient differential equation. We like those. Those are our favorite kinds. On the other side, there's some other stuff there. There's that 2x and e to the x. Now, what does that tell us? Well, that tells us that what we have is something which is not homogeneous. So this is a non-homogeneous differential equation. So, all right, so what does that mean? Well, that says we have sort of a generic game plan. So when we have a non-homogeneous differential equation, we find the homogeneous solution first, use that information to say, okay, what does the non-homogeneous piece look like, put them together, and since this one has initial values, once we have everything together, we'll actually solve for our initial values. Life will be good. All right, so let's begin with our homogeneous part. In other words, ignore the 2x plus e to the x. So we're going to say, all right, y double prime minus y equals 0. So we solve, and the way we solve is we turn this into a polynomial. This turns into the polynomial r squared minus 1 equals 0. So it has the roots 1 and -1. Now, that translates into solutions. So these roots correspond to things which show up in the exponents, namely, so 1 would correspond to e to the 1 times x. Our variable is x. Negative 1 would be e to the minus 1 times x, so that's minus x. And so we'll put them together, some constant plus some other constant. So that's our homogeneous solution. It's often denoted by y sub c, sometimes called the complementary solution. All right, so with that part out of the way, now we turn to the non-homogeneous part. So a good way to sort of start this portion is to think about what functions are involved. So if you just think about our functions, we see there's an x and there's e to the x. So those are our functions. And then we start going through our rules. So there's 3 rules. One rule is that if you have powers of x, you always have to have all the way down to 1. So the fact that we have an x says, oh, we better have a 1 involved as well. Another rule says sine and cosines come in pairs. Well, there's no sines or cosines, so that's fine. And our last rule says, look at the homogeneous solution and your non-homogeneous piece, and ask the question, is there any overlap? Well, there is. They both have e to the x. And if there is overlap, we need to somehow remove the overlap. But we can't take out, because then we're not going to be able to get what we need. But we can modify, and I call that the bump. So in this case, we bump by x. So what does this translate into? Well, what it translates into is that these pieces are going to make up our particular form. We already have a, b, so we'll keep working our way up our alphabet. So there's some constant times x, some constant times 1, and some constant times x e to the x. So that's what our particular solution looks like. Now, we're going to plug that into the left-hand side. And then we're going to gather and compare it to the right-hand side. So we'll need the second derivative. First derivative is not so bad. Constant, d goes away. Product rule, so we're going to have e times e to the x plus x e to the x. So in case you're wondering where did all that come from, product rule, right? Derivative of the first is 1 times the second. That's how you got e to the x plus the first times the derivative of the second. And the second derivative, okay, the constant goes away here. You'll get e to the x, and then same product rule that we just did, e to the x plus e times x e to the x. Okay, great. Well, if we now write what is y double prime minus y, well, in fact, we'll do, again, emphasizing we're plugging in our particular solution. Here, we have, there's 2e times e to the x plus e times x e to the x, subtract. And then our particular solution, c times x plus d plus e times x e to the x. And if we've lived a good life, things should simplify. Well, notice this part, the part that we bumped up, that will go away. In fact, that should happen. The things that show up because of the bumping should automatically drop out. And if they don't, something very suspicious happened here. Okay, not that we aren't always suspicious, but in this case, it worked out. So we have what? Well, we have 2 times e to the x. And then we have minus c times x minus d. Now, all of that is supposed to be equal to 2x plus e to the x. And now we start saying, aha, compare coefficients. So this 2e e to the x has to be the same as what's in front of e to the x. This minus c times x has to match with the 2, and the minus d, well, there's nothing for it to match with, so it better equal 0. So we come to the not very hard conclusion. Well, as we see, d equals 0. C, well, that has to equal minus a half. Oh, excuse me, not minus a half, minus 2. I can do math. And it's E where we end up with the half. All right, so our particular solution is, putting it in here, minus 2x plus 1/2 x e to the x power. All right, great. Now, are we done? No, but we've made great progress. We have our complementary solution, we have our particular solution, and if we put those together, we get our general solution. So that's where we're at. We now can say that our general solution has the following form. So y looks like some constant e to the x plus some constant e to the minus x minus 2x and plus 1/2 x e to the x. All right. Now, the last thing for us to do is our initial conditions. So we need to also have our y prime. So we'll also compute y prime. So that's a e to the x minus b e to the minus x minus 2 plus 1/2 e to the x plus 1/2 x e to the x. Plug the zeros in, and we see that y of 0, well, according to this, you get a plus b minus 0 plus 0. Oh, that's nice. Great. So all of that has to equal 1. Y prime is 0. What is that? Well, we get a minus b minus 2 plus 1/2 and plus 0. All right, so minus 2 plus 1/2. Well, we'll go ahead and write it all out. Minus 2 plus 1/2. And that all needs to equal minus 1. All right, good. Now we're to our really comfortable scenario, thing we've been seeing all semester. 2 equations, 2 unknowns. We can handle 2 equations, 2 unknowns. I hope we can. And so what do? Well, let's clean it up. This is the same as a plus b equals 1, and a minus b. Okay, if I add 2 to both sides, that would be a plus 1. Then I subtract 1/2, so that would be 1/2. So a plus b equals 1, a minus b equals 1/2. Let's just add those two together. We come up with 2a equals 1 plus 1/2 is 3/2. Okay, so that says a should be 3/4. Once we know a, that says 3/4 plus b equals 1. So that says b has to be 1/4. So now we know a and we know b. And those were the last 2 pieces of our puzzle. And so we are now ready to put it all together. So we're going to plug in value for a and the value for b. Plug into y. Plug in a, plug in b, and then the rest of it. So we get y is equal to 3/4 e to the x plus 1/4 e to the x minus 2x plus 1/2 x e to the x. And that's it. That's it. Other than I forgot to copy the minus sign there. There we go, right? Because there should be a minus x up in that exponent. All right. Wow. Beautiful. Beautiful. That's not so bad. We can do these, right? It's sort of a wonderful deja vu. It's like, hey, I remember this. I know how to do this. Because you do. You're good. All right, well, moving right along. Come to number 4. System. Solve the system of differential equations. X prime equals x minus 2y. Y prime equals x minus y. And with initial conditions, x of 0 equals 1. Y of 0 equals minus 1. All right, well, Now, I like to write systems in the generic form, so I'm going to think of our vector x. So this is, you can't really tell because of my handwriting, that's actually a bold x. So I'm thinking of this as being consisting of x and y. So sometimes people like to put a little vector symbol over that, or they'll just be like, okay, I'm just going to be really careful and work through context. So x prime would equal something times x. So this little matrix here is the coefficients. Now you might say, do we have to do matrix? No, it doesn't say. If it had said, for instance, using the eigenvalue method, yeah, you'd have to do a matrix. Matrices are where eigenvalues show up. Without a matrix, you could do things like substitution, but substitution doesn't really make the problem easier, I think. Once you have a system, especially 2 by 2, it's just as quick to do using eigenvalue methods. And so that's what I'd recommend. All right, well, let's find out what's going on here. So next step is we're going to take the determinant of a minus lambda I. And that's going to give us our eigenvalues. Well, it will if we set it equal to 0 and solve. So that's the determinant of 1 minus lambda minus 2, 1 minus 1 minus lambda. So we have 1 minus lambda times minus 1 minus lambda, subtract 1 times minus 2. All right. Well, what do we have here? Minus lambda times minus lambda, that's lambda squared. And then we'll have a plus lambda minus lambda cancels. It's no lambdas. That's nice. And then we're going to have a minus 1, and then we have a plus 2, right? So that makes it plus 1. Okay, great. So there we go. There we go. So lambda squared plus 1. All right. So, well, remember, we set that equal to 0. That says lambda is plus or minus the square root of I. So, all right, great. Wonderful. That means we have something which is a little bit complex. Well, that's all right. We know how to handle complex eigenvalues. All right. Do we remember how to do that? I hope so. I hope so. Here we go. So what do we do? Now, the nice thing is, once we know we have complex eigenvalues, it's like, oh, everything comes in pairs. See how we have like plus I and minus I. We're like, great, pairs, 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 pairs. So everything pairs up. So what about our eigenvectors? Okay, so we're going to look at a minus lambda I. All right, so that's 1 minus I, minus 2, 1, minus 1 minus I. And so I'm plugging in, this is lambda equals I. And I want to multiply it by some vector AB and get out 0, 0. So that's, here we're trying to solve for the eigenvector associated with the eigenvalue for I. Now, we know this as a fact, that for 2 by 2, what's going to happen is that there's going to be a redundant equation. And what we mean by that is we really have two equations. 1 minus I times A minus 2 times B has to equal 0. That's, if you like, that's the top equation. And then the bottom equation says A plus minus 1 minus I times B has to equal 0. That's the bottom equation. Like I said, one of them is redundant. And we can just pick which one we want. Well, no reason to just not pick the top. Why not? So what can this be? This would say, for instance, here, 1 minus I times A would equal 2 times B. That's what we need. So we just need choices for A and B where this works. So we say, hey, there's an easy choice for A and B that does this. Namely, you say, all right, let's let and let me choose a different color here just to emphasize what we do. We'll let A be the 2, and we'll let B be the 1 minus I. And so we get a choice that works, and we just need one. One choice that's not 0 that works is to get 2 and 1 minus I. All right, good. Now, that's our eigenvector for I. We don't need to do the eigenvector for minus I because we know it goes in pairs. So for minus I, the difference will be, it'll be 1 plus I. So how do we finish it up? Well, our next thing that we're going to do is to say, hey, we can combine our pairs in a nice way. And the way this works, and this is important to remember, so we're going to emphasize this. So we've done everything for I. So we know that our solution, well, it looks like e to the I t, right? So this is how the eigenvalue method works. It's e to the, whatever the root is, t, and our root is I, times our eigenvector, 2, 1 minus I. But now the magic. We say, wait a second, e to the it, we can rewrite that. That's the same as cosine t plus I sine t. And this 2, 1 minus I, we can rewrite that by saying, well, that's really 2, 1 plus I, 0 minus 1. Okay? So we're going to decompose that e to the complex root into two pieces. There's a real part and an imaginary part. We're going to decompose our eigenvector into two parts, real part and imaginary part. Now, the magic. And it's not, super magical in some sense when you see it. You're like, oh, okay, well, that works. But what you do is you say, okay, grab the real pieces. So in other words, you're going to take the cosine with the real part here and the real part here, the imaginary part with the imaginary part. And we multiply those together. And what we end up with is we end up with 2, 1 times the cosine t, and then I squared will be minus, and then we have sine t, 0 minus 1. All right, and now that's one piece, and then plus I. Now we do the imaginary parts. So how do you get the imaginary parts? Well, the imaginary parts, no surprise, we're going to associate the imaginary things. So we're going to take the cosine times the imaginary part and the sine times the real part. So we're going to end up with cosine t times 0 minus 1 plus sine of t times 2, 1. And now we say, okay, here's solution number 1, and here's solution number 2. All right, good. So, what does that tell us? Well, it tells us the following. We have that our general solution, xy, has the form some constant a times the first solution. Now, we can actually just put it into one vector. So that's 2 cosine t minus 0 and cosine t plus sine t plus b and solution number 2. Well, cosine t times 0 and then sine of t times 2, so 2 sine of t. And then we're going to get minus cosine t plus sine t. Okay, so those are our solutions. And now we come back and say, there's initial conditions. So when we plug in 0, x will be 1, y will be negative 1. So, at t equals 0, we have x of 0, y of 0 is 1 minus 1. And that will be equal to, a, and let's see, we get cosine of 0 is 1, and sine of 0 is 0. So we're going to get a times 2, 1. And here we'll get b times 0 minus 1. You might say, oh, 2, 1, 0 minus 1. Those sound really, really familiar. Yeah, they should. It's the real and the imaginary parts. Not a coincidence. Not a coincidence. All right. So that leads us to 2 equations and 2 unknowns. Yes. You will see lots of that. We should get really good at that. Okay, so the first equation reads off as 2a plus 0b equals 1. Well, great. That tells us a needs to be a half. And the second equation says a, so I'm reading off a times 1, minus b has to equal minus 1. Now, but we know a equals a half. So a half minus b is minus 1. So what does that say? Well, if you want, you can add 1 to both sides, add b to both sides, and we come to the conclusion that b has to equal 3 halves. So now we know a and we know b. All right. Now, let's be careful about finishing up here, because we can, if we have a very particular grader, and who knows who will be grading this. So the moral is we know that a is 1 half, and we know that b here is 3 halves. Okay, so we know a and we know b. So, but remember, what are we trying to solve? Let's solve the system of differential equations. The vector format and the matrix, that was introduced by us. And so what should our answer look like? Well, our answer should look like, here is x of t and here is y of t. So we should break it back down in terms of x of t and y of t, which is perfectly fine. So how do you do that? Well, you just read off our equations. So you see that x of t, that's going to be the top, 1 half times 2 cosine t. So that's cosine of t. And 3 halves times 2 sine t. So that would be plus 3 sine t. Y of t, what would that be? Well, 1 half times cosine plus sine, and then 3 halves minus cosine plus sine. Well, we can simplify that a little bit. So a half cosine minus 3 halves cosine would be minus cosine. 1 half sine plus 3 halves sine would get us to 4 halves sine, which would be 2 sine. And there we go. So, just because I'm running out of space, I'll be right over here. So we end up with x of t is cosine t plus 3 sine t, and y of t minus cosine t plus 2 sine t. And there we are. There we are. Great, right? We did it. We did it. Now, if we wanted to, we can check. How do we check? Well, check your initial values. If you plug in 0, we'll get 1 and minus 1. That's good. Well, probably it's not surprising that the initial values work, because it was the last thing that we did. We could even go through and say, well, does y prime equal x minus y? Well, x minus y would be what? Well, cosine minus minus cosine makes 2 cosine. And then here you'd have 3 sine t minus 2 sine t, which would be sine t. Okay, now what's y prime? Sine t, right? Root of minus cosine is positive sine. That's good. And 2 cosine t, which is exactly what we were saying it would be. Yay! So you can always check. One of the nice things about differential equation problems is that a lot of the times you can check your answer at the end, and especially if you're like, did I do this right? I'm not 100% sure if this is true. Well, find out. Find out. Do the math, as they say. All right. Number 5. So, for the system of differential equations, x prime equals ax, where a is equal to minus 2, 1, minus 4, 2, and x of 0 equals 1, 0, prove that a squared equals 0, and use it to find the exponential matrix e to the at. Finally, find the particular solution x of t for the system. Okay, well, we just need to do what it says. So, number 1, prove that a squared equals 0. Okay, so here we go. So a squared is minus 2, 1, minus 4, 2, minus 2, 1, minus 4, 2. And there's really not much here to do in the way of proving. It's really more of a check. But let's go through and do our check. So that'd be 4 minus 4, which is 0. Minus 2 plus 2, which is 0. Minus 8, positive 8, because minus 2 times minus 4 is positive. And minus 8, 0. And minus 4 plus 4 is 0. Okay, good. Now that's not so hard. Now it says, well, use it to find the exponential matrix e to the at. So now, okay, so we're in step 2. So we have that e to the at is the identity plus a times t plus 1/2 a squared t squared plus dot, dot, dot. But we know that a squared equals 0. And so what that tells us is a squared equals 0, but not only does a squared equals 0, this will all be 0 from starting with the a squared onward. So a cubed equals 0, a to the 4th equals 0. So we say, oh, well, that's really convenient. So the identity matrix, that's 1, 1, 0, 0. And then we have a times t. So plus minus 2, 1, minus 4, 2 times t. Put that together. 1 minus 2t, t, minus 4t, and 1 plus 2t. Okay. So that's e to the at. Great. Now there's a third part of this problem. It says find the particular solution for the system. So what's the key? Well, the thing is, this is e to the at, but we also know that this is a fundamental matrix, phi of t. In fact, this is phi of t, phi 0 inverse. This is like the fundamental matrix. And so the nice thing about fundamental matrices is it makes it really easy to solve. But the best fundamental matrix is e to the at. And so when we want to find the particular solution, that's step 3, what we have is the following, namely, we have that x is equal to e to the at times x0. Okay, well, we know what e to the at is. We just copy it down from what we just did. 1 minus 2t, t, minus 4t, 1 plus 2t. x0 is off the screen right now, but it's 1, 0. 1, 0. So we end up with 1 minus 2t times 1 plus 0. So 1 minus 2t minus 4t plus 0 minus 4t. And that's it. We're done. That's the whole answer. Wow. Oh, that's not so bad. And hopefully after the last exam, we're going to be like, we're going to get this one. No doubts. No doubts, no doubts, no doubts. All right. Well, that's number 5. Number 6. Use the Laplace transform table to find the Laplace transform of the following function. So it's a piecewise function. E to the 1 minus t if we're below 1, minus t if we're between 1 and 2, and t minus 1 if we're above 2. Now, I will point out there's a small technicality here that either the person who wrote the problem was not paying a lot of attention to, or they don't care. And we'll start the problem, and then we'll say, oh, here's the small technicality. Okay, but here we go. So how does this problem work? Well, what we have is we have a piecewise function. When you have a piecewise function, what you should do is to rewrite it in a way that's very, well, think of it as one-line notation. And so we're going to use the unit step function. And the key here is we have a change at 1, and we have a change at 2. And so that's why we need to pay attention to those two places. So what we're going to do is we're going to say, all right, let's write our function in the following way. So f of t is what's happening before our first change. So what's our function initially? So starting from time 0. And the answer is it's e to the 1 minus t. No big surprise. Plus, now we have a change at 1. And the way we do our change at 1 is we have a unit step function times t minus 1 times, well, we have our on-off switch. So we're going to turn off e to the 1 minus t, which means we subtract e to the 1 minus t, so that these would cancel. And then we're going to turn on minus t. So we're going to add minus t. So now those cancel. So at 1, we turn on minus t and we move forward. And then we go to our next change, which is at t minus 2. Say, okay, great. Now we're going to turn off what was happening before 2. So we're going to subtract minus t. And we're going to turn on what happens after 2. So we're going to add t minus 1. So turn off and on, right? It was on initially, then we turn it off. But we turn this on, then we turn it off, and then we turn this on, and we go forward. All right, so this is what it looks like in one-line notation. Now here's the subtlety. These are actually not the same function. Can you see why? They actually disagree at t equals 2. And so this is why there's a small subtlety. At one single point, they disagree. At t equals 2, it would think that you're actually into e to the t minus 1 in this format. Whereas in this way it's given, it would think you're in the minus t. That's why there's a super small subtlety. Now, in terms of the Laplace transform, it does nothing. So don't stress about subtlety. We don't care what happens at one point, unless you happen to be the delta function. Then we care a lot about what happens at one point, because the delta, it's just all about that one point, one moment in time. All right, but there's our function. Now, are we ready to take the Laplace transform? No, not yet. So there's a subtlety here. When we're taking the Laplace transform, we need to have everything matching what's inside the unit step function. So this t minus 1 says all of this needs to be written as t minus 1. Here, this t minus 2, all of this has to be written as t minus 2. So until we've done that, we're still waiting. And so let's see, what can we do? All right, so this will be, and I'm going to write this e to the 1 minus t. This is the same as e times e to the minus t. I'm just going to pull that apart. Plus unit step function, t minus 1. And here, I want to make this look like t minus 1. Well, it's so close. So we'll write it as minus e minus t minus 1. Okay, that's fine. That fixes that. Now here, I want this to look not like t. I want to make it look like t minus 1. So right now, it looks like minus t. So say no problem. Make it look like minus t minus 1. But now it doesn't match. How do we fix that? Well, it's currently saying, oh, plus 1. That plus 1 shouldn't be there. Minus 1. And then we're good to go. Okay, so now we come to the next part. U, t minus 2. Here we have t, but again, we have to make it look like t minus 2. So we say no problem, t minus 2. We say, whoa, hold on, you put minus 2 there. All right, well, we fix it, plus 2. Now, the last part, this e to the t minus 1. We want it to look like e to the t minus 2. So this should really be e to the t minus 2. Now, I'm going to do some work on the side here, just because we're so close. I just want to make a little note here. I'll work up here, where we have a little bit of space. So e to the t minus 1, that's the same as e to the t minus 2 plus 1. And that's the same as e to the t minus 2 times e to the 1. Because you can think of it as saying, hey, I can change, addition becomes multiplication. So we are also going to have times it by e. And e is a constant. And constants are fine for us to work with. Now we're great to go. Everything looks like the right format. So because we had these unit step functions, we rewrote our functions to match what step functions do. So in other words, t minus 1, everything here looks like a t minus 1. There's a t minus 2, everything looks like a t minus 2. I pulled off my constants as I needed to. Now I'm grabbing my formula sheet here, and let's see what we have. Well, e to the at, 1 over s minus a. Now the e is a constant, so this e will just stay as e. And so this e to the minus t, that's a equals minus 1, becomes 1 over s minus 1, or 1 over s plus 1. Okay, so let me switch colors here, because now we're doing the answer. So we have that the Laplace of f of t is e times 1 over s plus 1. Now, the u of t minus 1, what will happen is we're going to go through everything, and then we're just going to have an e to the minus s, because that's what it says. If you have u of t minus a, and everything looks like f of t minus a, well, just take the Laplace transform of the everything else times by e to the minus s. So what happens? Well, so we're going to have plus, and then we just go through term by term. So this again is essentially e to the minus t. So minus 1 over s plus 1. This would be the Laplace transform of t. And let's see, does that show up on our list? Laplace transform of, well, t to the n shows up. Laplace transform of t would be 1 over s squared. And so minus 1 over s squared. And minus 1 is 1 over s. And that's all times e to the minus s. Okay. Now, same thing there. T minus 2, 1 over s squared. Plus 2 times 1 over s. And here we have e to the t minus 2. Well, think of this as e to the t is what we're queuing off of. And there's a factor of e, so we have plus e times 1 over s minus 1. And this is e to the minus 2s. So do this carefully. See, if it's e to the at, 1 over s minus a. So e to the t would be 1 over s minus 1. So e to the t. Now you might be saying, but what? That's t minus 2. But remember, it's u of t minus a, f of t minus a. So now we're thinking of, okay, so that t minus 2, because everything here has t minus 2, think of it as just like t plus 2 plus e to the t times e in terms of running the computation. And then multiply by e to the minus 2s at the end, which is what we have. All right, and that's it. Wow. Whew, we actually fit that. That wasn't so bad. I was worried we wouldn't be able to fit that in, but we did. We did. Mostly it's just a matter of saying, do you know how to rewrite that piecewise function? And then just cleaning it up. Okay, now we're ready for part B. The inverse Laplace transform. Oh, we might have a challenge fitting this one in on this piece. Now, first thing, before we get too far, this is going to be partial fractions, but so many students made mistakes on this. I want to just emphasize, you need to not do the mistake. And that mistake is the e to the minus 2s is not part of your partial fractions. So your partial fractions is going to be with the 50 over s plus 1 squared times s squared plus 9. And then the e to the minus 2s is off to the side. So this is what we want to do the partial fractions on. And this we're just going to have after we finish our partial fractions. Okay, so now we're ready to get going. So this is just a note for me later on when I'm looking at my solutions again, wondering, well, what was I thinking here? I was thinking, yeah, let's do partial fractions. Oh yeah, I agree with that. That sounds like a great idea. Sounds great. So there's a couple of small things you have to think about with partial fractions. And sort of the most challenging is just saying, do I have the right form? And then how do you get the right coefficients? So you have an s plus 1 squared. So we're going to build up. So you have an s plus 1, and you have an s plus 1 quantity squared. And these will be constants upstairs. And then here, the s squared plus 9, we only have one of those, but that's an irreducible. So there's a cs plus d. And you should check. Well, it's fourth degree if you were to multiply it all out. And there are 4 unknowns. So that's a good sign that we have it set up right. Now, the next thing, and a few people made this mistake, and I'll just point it out here so that, even fewer make the mistake. When you're clearing your denominator, it's not multiplying by all of these. This part is what you use to clear your denominator. So s plus 1 squared times s squared plus 9. And, all right. So when we do that, we end up with the following. 50 equals, so in the first piece, one s plus 1 cancels, but only 1 does. So you get a times s plus 1 times s squared plus 9. In the second piece, both s plus 1 squareds cancel, b times s squared plus 9. And in the last piece, the s squared plus 9 cancels, so you get cs plus d times s plus 1 squared. All right, well, I like to make good choices. For example, being in differential equations. What a great choice! So let's talk about some good choices that we can make. If we have any. Do we have any? There's at least one good choice, right? We could choose s equals minus 1. And if we do that, we'll get 50 and 0, 0. The right term that's not 0. We have b times 10. So, okay, that says b equals 10. Great. Good choice. Wonderful choice. Now, if you're very sophisticated, you could say, choose 3i. That's a little bit more complex than I'm comfortable doing. So I'm not going to do that. And so now I'm going to go into phase, not good choices. I don't know what to call it. I'm going to look at coefficients of polynomials, which means I get to distribute. So if we go through here term by term, so the first piece would be a, then s cubed plus s squared plus 9s plus 9. Okay, that's the first one. And then we have plus b times s squared plus 9, that's no surprise, plus c times s plus d, and s squared plus 2s plus 1. All right. Well, that's, well, let's keep this piece going. So that would be c times s cubed plus 2s squared plus s, and d times s squared plus 2s plus 1. All right. And I'm about to run out of space here. So I'm going to grab a blank sheet of paper. Scratch paper, right? We're allowed to use scratch paper on exam. Yeah, absolutely, absolutely. Okay. I can't believe I got this wrong. 50 equals 10 times b is really saying that b should equal 5. Okay, well, better late than never. So here we go. Okay, so 50 is equal to, and now we're going to group coefficients. So s cubed, and where do we see s cubes? There's an a, nothing. There's a c, nothing. So a plus c. Then we have a s squared, and where do we see s squared? So we see an a, and then we see a b, and there's a 2c, and there's a d. Oh, there's lots of s squareds. Okay, how about for s's? What do we have? We have plus s's, we have 9a, and then we have 9b. Oh wait, no, that's a constant. We're doing s's. We have a plus c, and we have a 2d. Now we're just to our constants. So that's where we have a 9a and a 9b. And there's nothing for c, and then there was a d. Okay, good. And we had, for making good choices, and if we can actually do our math right, we have this little side note. We know that b has to equal 5. All right, now, how do we use this information here? Well, what we do is we solve for our coefficients by saying, well, wait, things have to match. So a plus c has to equal 0. A plus b plus 2c plus d has to equal 0. 9a plus c plus 2d has to equal 0. And 9a plus 9b plus d, well, that better be 50. All right. 4 equations, 3 unknowns. Well, 4 unknowns. But that's really down to 3 because we already know b. So we're 1/4 the way there. Woohoo! 1/4, 1/4, yes! But actually, that helps us a lot. So for instance, we can say now that a has to equal negative c. Now, notice this equation. That only involves a, c, and d. So what does that one tell us? Well, if a equals negative c, we have minus 9c plus c plus 2d has to equal 0. Well, that's minus 8c plus 2d equals 0. Or we could say that 2d has to equal 8 times c. Or that says d has to equal 4 times c. So now we know a and d in terms of c, and we already know what b is. B is just 5. That means we really if we can just figure out c, life is good. And so now we've used the equation for s cubed, we've used the equation for s. Pick one of these, doesn't really matter. Let's suppose we pick a plus b plus 2c plus d. So minus c plus 5 plus 2c plus 4c equals 0. So, a and b and 2c and d. But I'm using the facts we know about a, b, and d. Well, we add, there's 6c minus c. So that says 5 plus 5c equals 0, or c equals negative 1. So now let's compile. A, B, C, D. So C equals negative 1, B equals 5, A equals negative C, negative negative 1, positive 1, and D equals 4C, so that's minus 4. Now, we can check using this equation because we haven't used that equation yet. So let's see, do we get 50 out? And if we don't, we should really think about it. 9 times 1 is 9. 9 times 5 is 45. That brings us up to 54. 54 subtract 4 is 50. All right. Good, good. On a side note, you may have noticed there was a video edit just a few minutes ago. I made some mistakes, but I could see things weren't working out, so I said, aha, I'm going to redo it. You should check your work. If things don't work out, if the equations don't work, don't just be like, well, I guess I'll keep going, hope for partial credit. No, we want all the points. Got to get them all, got to get them all. So if you see things are wrong, start backtracking and ask yourself, hey, where did we go wrong? And no, it was not signing up for this class. That was not a mistake. Now, we're not done. Where are we at in this problem? Well, what we've been doing is partial fractioning. So now we know how to rewrite this expression in terms of pieces, A, B, C, D. So we're going to rewrite it. All right, I'm going to glance over at my notes here. So we have our expression. So we have A over S plus 1 plus B over S plus 1 quantity squared plus C times S plus D over S squared plus 9. And all of this multiplied by e to the minus 2s. Okay, so again, I'm plugging in A, B, C, D into this expression, and there's that e to the minus 2s involved. Okay, are we done? No, because our goal is to take the inverse Laplace transform. So the last thing for us to do before we actually do our inverse Laplace transform is to clean this up a little bit. So 1 over s plus 1, I'm just going to pull out some constants here, 1 over s plus 1 squared. And this s squared plus 9 is actually pretty nice, so I'm going to break it up. So as s over s squared plus 9. And then as 4 over s squared plus 9. But then we're going to ask the question, what would we really like upstairs? So this is when we go back and say, hey, we know our table. And our table says when you have an s squared plus a squared, let's see, where do we're looking? So s squared plus a squared, if we have a constant upstairs, we want it to be a. So if it's s squared plus 9, that's 3 squared. We want to have a 3 upstairs. So we're going to put a 3 upstairs. But then we just put an over 3 in the front. Now, here's one last piece of our puzzle, which is to say, what happens to these little individual things? Now, 1 over s plus 1, that would correspond to what? Well, that's 1 over s minus minus 1, so that's an exponential function. So this would be e to the minus t. 1 over s plus 1 squared, that looks a lot like that part, where we use a equals minus 1. So it's t e to the minus t. So this part right here would look like t e to the minus t. S over s squared plus 9, well, that's cosine 3t. And just to save ourselves work, a over s squared plus a squared is sine of 3t. So this looks like cosine of 3t. And this looks like sine of 3t. Great. Except, be careful, because we see that e to the minus 2s. So when we see e to the minus 2s, we know that that corresponds to the unit step function turning on. So we say, okay, we're going to take the inverse Laplace transform of all of those, but then we got to shift. How much? Well, if it's e to the minus 2s, that says we turn on at 2, and we shift by 2. So our final answer is the following. So we're shifting by 2, so our unit step function, t minus 2 times. Now, everywhere where you see t, just make sure you have t minus 2. So e to the minus t minus 2. Don't forget there's a 5. T minus 2. E to the minus t minus 2. Minus cosine of 3 t minus 2. Minus 4/3 sine 3 t minus 2. And there we are. Whew, wow. That's a lot of work. Well, and that's only half of a problem. But what a problem, what a problem. All right, good. Well, at least we got it. At least we got it. I would say that one's probably a little bit more challenging than what we would expect to do on an exam. I hope. I hope. So we have the following. All right, so y double prime for s squared y of s, and the other terms go away. They're 0. Don't forget to do the y. Some people did. Well, we're not going to do that mistake. Y of s, sine of a half t, would be 1/2 over s squared plus 1/2 squared. Delta t minus a half, well, that's e to the minus 1/2 s. And delta t minus pi halves, e to the minus pi halves s. Good. And the initial conditions are showing up in that there's nothing here. And so we like zeros as initial conditions. Makes things a little bit nicer. A little bit, yeah. Okay, so we have on this part, well, this is 4 s squared plus 1 y of s. Okay, so let's move that over. And, as they say, notice something here. I could pull out a 4. So this is also the same as 4 times s squared plus 1/4 y of s. And the reason I say that is, hey, that's an s squared plus a 4th. That's suspicious. So very, very suspicious. Okay, so what do we get? We get that y of s is equal to, well, the first term will be 1/8 1 over s squared plus 1/4 squared. And then we have plus 1/4 1 s squared plus 1/4 e to the minus 1/2 s. Not plus, minus 1/4 s squared plus 1/4 e to the minus pi halves s. Now, these aren't going to be too bad. S squared plus a 4th squared. Okay. All right. We're going to try something here. This should be making us start to sort of freak out. Because s squared plus a squared downstairs does exist. But either we have to have a 2sa or s squared minus a squared? We have neither. Neither. So, that's not good for us. So we're going to bite the bullet here and try to figure out what that should be. All right, and when I say try to figure out what that should be is, what's the inverse Laplace transform of that beast, if you will? So here we go. We're going to be going way down the rabbit hole here. And so in case you're thinking to yourself, is this really what we're going to be expected to be able to do? The answer is no! No! When we wrote this test, or whoever wrote, I did not write this test. When they wrote it, they were like, oh, this one will be fine, no problem. No. They didn't try it. They just wrote it. And things like this happen when you just write stuff. Okay. So, here we go. I'm going to focus on trying to figure out what's the inverse Laplace transform of that one expression. Okay, so I am going to think this as 1/2 times 1/2 over s squared plus a half squared, and 1/2 over s squared plus a half squared. And about 2 pages later, we'll make progress. Now, why am I thinking of it in this way if my goal is to find the inverse Laplace transform? Well, because there's this fun little fact right here. F of s times g of s is f star g, which means products become convolutions. Okay, so time for us to jump down our rabbit hole. This is our f of s. This is our g of s. And so, according to this will go to 1/2 of, well, we'll write it as f star g. Now, we should note what is f and what is g. So, where f is going to be, if we just took the inverse Laplace transform of that. Now, that is set up to be sine of a half t. And again, g is sine of a half t. And now we're like, oh, great. So all we have to do is find f star g and life is good. So let's do a little bit of a recall. And, well, it's good for us to recall things. F star g, this is convolution, is integral 0 to t f of tau g t minus tau d tau. So when you see an integral like this, that's convolution. And convolution is nice because we can go from something which is convoluted to multiplication. Well, actually doing a convolution, though, might take us a few minutes. So let's be patient and feel free to skip forward about 20 minutes from the following computation, because we're going to just jump back into the previous computation and go from there. So we have 1/2, which is our constant in front, and we're going to do integral 0 to t and sine 1/2 tau and sine 1/2 t minus tau d tau. So that's our computation that we need to carry out. So we're going to be pulling out trig identities. And again, I'm going to say this just 1 or 2 more times. This is not what we had expected. You would not be expected to do this on an exam. This is what happens when you write problems and don't try them before you give them to other people to try. Small changes in a problem can turn something very simple, something obnoxiously hard. And we prefer to avoid that. So there's this nice fact. And I'll write the general fact over here. So sine of a minus b, which is what we have here if we work the 1/2 through, is equal to sine a cosine b minus sine b cosine a. So in other words, it's pretty straightforward to take a difference of the sine function. So what that tells us here is that we're going to have sine of 1/2 t times cosine 1/2 tau, and then minus sine 1/2 tau cosine 1/2 t. So that's what's going to happen. And we distribute that sine of 1/2 tau through. So we have 1/2 integral 0 to t, and well, we have sine of 1/2 t, and then we have this expression, sine 1/2 tau cosine 1/2 tau. We'll come back to that. And then we have minus cosine 1/2 t, and then we have sine squared 1/2 tau. And we're doing this integral d tau. So now we go to power reduction. And these are things that we don't need to have that formula because we know power reduction. So sine theta cosine theta is basically sine 2 theta, except there's a factor of 1/2. So this part right here is 1/2 sine 2 times 1/2, so 1/2 sine tau. Sine squared of something, well, this would be 1/2 1 minus cosine, double the angle, so cosine would be tau. All right, so our power reductions. Now, what can we do? Well, we can pull out the halves all the way out in the front, so we'll do that. So we have a 1/4, so pull out the half, and then we have the integral, 0 to t, and we have sine 1/2 t sine tau. Then we have minus cosine 1/2 t, and plus cosine 1/2 t cosine tau. All right, d tau. And now we're ready to integrate. So this is 1/4. Remember, everything with the t is a constant because we're integrating with respect to tau. So it's just the sine tau, the cosine tau, and this is 1. All right, so integral of sine minus cosine. So minus sine 1/2 t cosine tau. Here, minus cosine 1/2 t tau. Integral of cosine, positive sine. Cosine 1/2 t sine tau. Evaluate 0 to t. Now, in case you're getting confused here, I'll throw in my parenthesis that I haven't been throwing in so far. So those are the parentheses that would be there. And remember, we're talking about tau. So tau equals 0 up to tau equals t. So we'll plug in tau equals t. And what do we get? Well, we get 1/4. Here we have minus sine 1/2 t cosine t minus t cosine 1/2 t. And well, that's nice. Plus And let's see where we're at. Cosine 1/2 t sine t. Okay, that's plugging in t equals tau. Subtract 0. Now sine of 0 is 0. 0 is 0, but cosine of 0 is 1. Subtract. So we're subtracting it. So minus minus makes plus sine 1/2 t. Okay. Good. All right. Did you see that? So this is, again, this part here. This is tau equals t. And this part right here, tau equals 0. All right. Now we're almost in the home stretch. And you're just thinking like, what? And keep in mind, this is just one little piece. Okay, equals 1/4. Now, let's stare at this for a second and see what we have. Does it look like anything we've seen before? Like this. We've seen that before because we see it right now. It's like sine A cosine B. So sine A cosine B minus sine B cosine A. So that, if we combine these two terms together, that becomes sine of t minus 1/2 t. So that's these terms combined. And then we have a minus t cosine 1/2 t and plus a sine of 1/2 t. But t minus 1/2 t is sine of 1/2 t. And so we can add it to there. So what we end up with is 1/4 2 sine of 1/2 t minus t cosine 1/2 t. All right. Okay. I know. I'm feeling the same thing you're feeling. I'm feeling like, what? So the thing is, we didn't actually have it on our table. And I swear to you, this is not what we intend for you to think of when you try to take your exam. It's not going to be anywhere close. But it was fun. We got to do convolution. That's not a bad thing to know. Convolution. It could save your life. Well, maybe it could save a few points on the exam. But in terms of like the actual computation, this is way past what we'd expect you to know. Okay. Let's get back to our problem. Okay, so coming back to our problem. What do we have? Well, the thing is, let's rewrite what we have for y of s. So y of s, well, we have this piece in front. We will leave it as it currently is because we know how to handle that. Now, we want to make this of the right form. Well, what that means is we want to have a half upstairs. So we're thinking of this as a 1/2 times 1/2 over s squared plus, again, a half squared, e to the minus 1/2 s. Do the same thing here. Minus 1/2, 1/2 over s squared plus 1/2 squared, e to the minus pi halves s. And now we go through and say, what happens to the pieces? There's going to be a shift. We'll worry about the shift in a moment. But without the shift, this piece right here, this is sine of 1/2 t. And this piece right there is sine of 1/2 t. And, all right, we'll make a note. Here we have shift, And over here we have a shift. And this first part, this hard fought for piece, that's this page. So that's this 1/2 times half times half. So that's the 1/8. 1 over s squared plus a, whoops. There we go. S squared plus a half squared. Yeah, there we go. Anyways, the point here is that turns out to be that value. So we're just going to copy that. So that's 1/4 2 sine 1/2 t minus t cosine 1/2 t. Okay. So now we're ready because we know how to do the inverse Laplace transform. So we get that y of t is equal to, well, this first piece, we can distribute the 1/4 through. So 1/2 sine of 1/2 t, and then minus 1/4 t cosine 1/2 t. Okay, that's the first piece. Then there's a plus a half. And because we have the shift, unit step function, t minus a half, and sine of 1/2 t minus a half. Okay, and then this other piece, well, we're running out of space, so we'll just write on the next line, minus a half, again, unit step function, t minus pi halves, sine of 1/2 t minus pi halves. And there we are. Done. Nice and easy. Nice and easy. Sure, if you have that part, which was not on our sheet, well, what can you say? Sometimes things take a little bit more effort, but it worked out. It worked out. All right. Okay, that was a good workout. We need a nice cool down. So, our last problem, our cool down. Find the recurrence relation for the coefficients of the series solution around x equals 0 for the following equation. And form the series solution to the equation with the first 7 terms until the term for x to the 6 with c0 and c1 as 2 constants. And our equation is xy double prime minus y prime plus y equals 0. Okay? Now, it looks pretty harmless, right? This is, oh, okay, nothing so bad. Except, things are going to happen that kind of break it. And I want to point this out before we even start, that we can't really answer this question, or even if we got an answer, it's kind of not a good answer. Okay, so what's going on here? Well, we're talking about a series solution around x equals 0. All right, nothing wrong with that. That's perfectly fine. And what's the issue? Well, the issue comes if you look at that little piece right there. That x in front of the highest derivative, x, y, double prime. Now, what does that x tell us? Well, it tells us the following. We now can say, hey, you know, x equals 0 is a singular point. And, all right, well, you might say, what's so bad about that? Well, once we have x equals 0 as a singular point, we can say, well, that means that we expect our radius of convergence. In other words, you know, how far would we expect our answer to work? It'll be 0. Now, if your radius of convergence is 0, it basically says, hey, if you do succeed in getting an answer, which you may not, it's not going to be a useful answer. Unless by some miracle, the stars align and things cancel so quickly that it's not an infinite polynomial, but you know, the terms actually stop at some point. Now, you have to really be lucky to get the stars aligned like that. It might happen. I doubt it. But, well, okay, we'll keep going, and let's see what we have. Now, the process is very straightforward. It's the kind of process we see all the time. We say, all right, well, let's talk about y. It looks like a sum, namely 0 to infinity of c sub k x to k. And y prime is very similar. We just take the derivative of each piece. We get k, c sub k, x to the k minus 1. And I think we can squeeze in y double prime. I hope. Maybe. Maybe not. Oh, we're going to be close. The sum 0 to infinity, it's k minus 1, ck x to the power k minus 2. All right, we didn't really fit it in, but imagine we had. No, okay, let's not imagine. Let's just write it again. We have the patience. We can write it again. All right, k minus 1, ck x to the k minus 2. All right, now the next step is we're going to plug y prime, y double prime in for the appropriate expressions, and then we'll clean it up. Okay, so we have the following. X times y double prime, and so that's the sum. You'll notice on these problems, a lot of this comes down, no one single step is too bad. It's just copying. Copy. All right, be patient. Work it out. And, okay, so x times that sum minus the sum, k equals 0 to infinity of k, ck, x to k minus 1, plus the sum 0 to infinity, c sub k, x to the k equals 0. All right, great. Now, well, not much to do. We just have to bring this x inside. And, okay, well, that won't be too hard. So the only thing that'll happen in our next line is that in the first term, the x to the power k minus 2 will become x to the power k minus 1. All right. So we'll have the sum 0 to infinity of k minus 1, ck, x to the power k minus 1. Now, one nice thing you'll notice is in the first term, we do have a power x to k minus 1, and in the second term, we have x to k minus 1. Nice! So that's a really good thing. And the reason I say it's a really good thing is it means that it's going to be easier to get things to put together. Sometimes, like, all the powers are different, and it's like, it's going to be a little hard to smoosh it all up. Oh, that's okay. Not this time. Not today. We're going to make it. We're going to make it. And, well, okay, we re-index, or if you like, change our names, kind of like what we do in substitution. And so in the first term, we're going to make the power, which is k minus 1, we'll call that L. Same for the second. And the last one, we'll just, hey, the power is already good. We'll just change the name, call it L. All right. If L equals k minus 1, k equals L plus 1. And that's true for the first two. So we have in the first sum, L equals, well, let's think about it. Now, if k equals 0, L equals minus 1, that's kind of a weird place to start. But notice something. The first term here is automatically going to be 0. So what we'll do is we'll say, look, just pull off the first term, which is 0, and start at 1. And we can do that with the second term as well. Okay, so now, if we do that, well, 1 minus 1, 0. Great. To infinity. Then we're going to get k becomes L plus 1. K minus 1 becomes L. C, and L plus 1. X to the L plus 1 minus 1 is x to the L. The second sum, something very similar. L equals 0 to infinity. And we're going to get L plus 1, C, L plus 1, x to the L. And the last sum, we basically recopy it. The only thing that happens is wherever we see a K, we put an L. Okay, good. Now, the nice thing is, all the sums start at the same point. All the powers are x to the L. We can all smush it together. One sum to rule them all. All right, so if we do this, and we're going to have the sum L equals 0 to infinity of, well, L plus 1 times L C sub L plus 1. That's from the first term. So L plus 1 times L C L plus 1. Subtract, then L plus 1 C L plus 1. And then subtract, whoops, why is it subtract? It should be plus. Typo. Oh no, quick, fix it. Boop. All right, see how easy it is to fix typos? But see how also easy it is to make typos? All right, be careful. A lot of this is copying, and so you just got to make sure as you copy faithfully. And that's a lot of places where people lose points. There's small errors in the copying. And now our great aha is the following. It says, hey, compare the coefficients on the left and right hand side. And you might say, well, there are no coefficients on the right hand side. Exactly. They're all gone, which means they're 0. All right, well, that means that all of these coefficients over here also have to equal 0. And so this is going to be where we get our recurrence relationship coming from. So, all right, great, no problems. We can do that. Now, let's work out what that recurrence relationship actually says. So, notice we have two terms with CL plus 1. Now, that's not so bad in and of itself, but let's group the coefficients. You have L squared plus L, subtract L plus 1. Now, you can think of it as L squared plus L, subtract 1. The L's cancel, and so we can say, oh, this becomes L squared minus 1 times CL plus 1. And then we have our plus CL is equal to 0. Well, okay, we can move that over and divide, and we come up with CL plus 1 is minus C sub L over L squared minus 1. And there's our relationship, and we'll say this holds for when? Well, starting at 0. So for L, at least 0. Okay, now at this point, you're probably like, okay, all right, Steve. This looks great. Why were you making such a fuss? This seems unfussy. There's nothing bad going on here. Or is there? Let's take a look. So, now notice this relationship is always true. So we can plug in any choice for L. So let's plug in some small choices. If you plug in L equals 0, what do you have? Well, you have C1 is minus C0 over minus 1, right? Because you get minus C0, 0 minus 1 is that, or it's equal to C0, which says, hey, wait a second, C1 and C0 aren't free choices. Whatever you choose for C0, you have to choose for C1. But in the problem, it said, hey, you should think of C0 and C1 as two constants. What? What's going on here? That's not a good sign. It's not. Okay. All right. But we keep going. All right, so that's L equals 0. Well, what about L equals 1? What does that tell us? Well, it says C2 is equal to and minus C1 over 0. Now, in case you're wondering, what does that mean? That means, oops, that's not good because you can't divide by 0. Now, for the purist in the room, you might say, well, we could do the following. Okay, I'm listening. We could say C1 equals 0. Okay. And then C2 is a free choice. All right. So at this stage, the only way this could work is if both C0 and C1 were 0, and if C2 were a free choice. Now what happens? Well, from here on out, you can keep going like you would normally. You can say, oh, okay, well, then from L equals 2, what would we have? We'd have C3 is minus C2 over 3. And we could say, okay, the next one, well, would be L equals 3, which says that C4 is minus C3 over, let's see, so we're doing L equals 3. 3 squared minus 1 is 8. Okay, that's the same as C2 over 24, and so forth and so on. But the problems are, look, we were wanting to get it in terms of C0 and C1 as two constants. No, it has to be 0. And C2, okay, that's a free choice. And then you're like, okay, well, all right, Steve, I'll live with that. But what else do we see? Well, the problem is, well, we get this expression. When do we expect it to be true? And well, because 0 is a singular point, we can start building things up, but we expect the radius of convergence to be 0. We don't expect it to work. And so basically, this oops is a big oops. So it kills the problem. So it shouldn't have been asked in the first place. So the problem falls apart. Sorry about that. Sometimes that happens, but that's all right. At least we got good practice in solving for a recurrence relationship, and that's a good skill to have. All right. Well, keep practicing. Don't worry. On the real test, we'll check it more closely. All right. See you later.